Good morning, students. So, in the last two sessions, we have started with chapter number 2, which is 8051 Assembly Language Programming. We have seen different instruction set. Then, in the previous session, we have seen the looping concept and the jump concept or the branch instructions. Now, in the today's session, we will be seeing call instruction and the other timing delay concept. Okay, so let's start with the call instruction. Call instruction is used to call the subroutine. Subroutine are used to perform specific tasks that have to be performed very frequently. This makes the program more structured and it saves the memory space. The first instruction in call set is lcall. Lcall means long call. This is a 3-byte instruction. First byte is opcode, second and third byte are for the address of target subroutine. Subroutine is located anywhere within 64K byte address space. A call is absolute call. Absolute call is a 2-byte instruction. Only 11 bits are used for address which is within range of 2 kilobyte range. So this is just similar to long jump and short jump. We have long call and absolute call. The difference here is created in terms of the target address size. So now first instruction is L call, long call. When a subroutine is called, control is transferred to that subroutine and the processor will save the address on stack. The processor saves on the stack the address of the instruction which is returned immediately below the L call. And now the processor will begin to fetch instruction from the new location. After completing the execution of subroutine, the instruction RET transfers control back to the call. Every subroutine needs RET, that is return instruction, as the last instruction. So basically how this call instruction works, whatever address you will define after L call, it will jump to that call address, and meanwhile whatever next instruction is kept after L call, the address for that next instruction will be saved on stack. Once this calling operation or specific task which has been called at that address is completed, it will again return back to the program and it will resume the program from where we have left. That is the next instruction. Address will be saved in stack and from that address the program execution will begin again or it will resume again. So for that operation we need to use RET instruction so that it will help to resume the task which was left due to call instruction. So RET will return back to the address from where the execution was left. So let's take the example here. Now this program is given to you. ORG0 originating address is 0. Move A 55H. A accumulator is loaded with data 55H. Now move P1 comma A. So port 1 is loaded with the data of A, that is 55H. Now L call delay. So now the delay loop will be called. So where is the delay loop here? So after L call delay, this instruction will go to the delay loop and it will start executing this instruction which is mentioned in delay loop. After ending of this delay loop, we have to write RET instruction so that it will return back to the instruction from where we have left. Whenever L call is executed, the address of instruction below it, which is here move A, 0 AAH, is pushed onto stack and 8051 will start to execute at this 300H. So once this delay loop is over, your delay loop runs 255 times. FF is the maximum limit, so it will run 255 times. Once it has run 255 times, then after that it will go at RET instruction. What RET instruction will do? When R5 will become 0, control falls to the RET instruction. It will pop the address from stack. Initially, we push the address of next instruction on stack. Once this operation is over, now we have to pop it back. Pop it back means you have to fetch that address back from stack into the program counter and you have to start executing the instruction from where you left. You have to resume the execution of instruction after call. So this way the subroutine works. If you have any query, you can ask me related to this topic. This is a very important topic, and in GTU exams also few questions are asked related to jump, loop and call instructions. So students, please keep this topic in your mind and do refer to this video many times, and if you have any query you ask me and try to clear this topic efficiently. So here we can see how the address is pushed into stack. Let's see now. After executing the L call delay instruction, you have to push the address of next instruction into stack. Stack is a register. You all know that SP is the stack pointer register. You have to save the data in stack pointer so that after returning from this call operation, you can again start or you can resume the instruction or resume your program from where you left executing. So here the next instruction addresses 0007. So lower byte 07 will go first in stack. Again stack will be incremented and at higher address, higher byte will be saved. So now in pushing the address, lower byte is gone first and then higher byte is loaded. While at the end of this call instruction, whenever we are doing return operation, at that time we have to again fetch this address so that we can resume our execution. So now at that time, the higher byte will come first out and the lower will come second. You understood? The way it has gone inside, it will come the same way outside. Initially lower byte loaded, then higher byte loaded. Now if you want to make this address come outside, then at that time stack will be pointed at this address only. So it will fetch the higher byte first and then the lower byte. This is the example of push and pop. Normally in any subroutine example, number of push and number of pops should be same, because the number of times you are pushing the data on stack, the same number of times you have to pop it out from the stack. So this is example of push and pop in subroutine. Push instruction will push the data into stack pointer and pop instruction will take the data out from stack. So push is like pouring water in glass. and pop is like throwing the same water out of the glass. So this is the analogy of push and pop instruction. These instructions are very frequently used whenever you are writing any subroutine program. This is the syntax of writing or calling a subroutine. It is common to have one main program and many subroutines inside the same main program. This will allow you to make each subroutine into separate module. Each module is tested separately, and if you have any error, then you can easily decode it. In a large program, the module is assigned to different programmers, so all programmers can check their subroutine part and can verify the program easily. So this is the format of writing a subroutine. Now the next instruction is a call. The only difference between a call and L call is the target address of L call is larger. It is in range of 64 kilobyte, while a call, which is absolute call, is in range of 2 byte only. The use of a call, which is absolute call, is done instead of long call or L call to save the space. To save the number of bytes of ROM space, you can use absolute call instead of long call. So these are the examples of L call and A call. In the first program, your long call is used, and in the second program, your absolute call is used. You can see the length of program is longer using long call, while the same program which is written here has been efficiently rewritten here using absolute call with few syntax only. So this way absolute call will work. Now the next topic is how to calculate time delay in 8051. This we will see in the next session, and we will be calculating the time delay or the machine cycle or clock cycle which are required to execute or to implement any instruction set. That will be part of this timing delay topic. Again, this topic is the most important topic, and one or two questions are definitely asked in exam from this topic. So all of you, please pay attention in this topic. We will continue with this topic in the next session. You revise call instruction, jump instruction, looping concepts. So in the next session, we will move towards the time delay for various 8051 microcontroller. Thank you.